Hello, this is Module 1, where we'll be learning about concepts of measurement. Our objective in this lesson is really to start learning the theory behind scientific methods, and this will lead us into how statistics are used and how they're used to test our understanding of the world around us. So in this module, we'll be covering the scientific theory, just a general introduction. Then we'll talk about how we use data, explaining various different data types, which now you've had a little bit of exposure to from the first module, learning different Python syntax. This will help us then explore how we can describe these variables and the different types of measurement scales that we can use. And then lastly, we'll inspect and explore some data. So in this module, we'll have a presentation that I will start shortly. We have 2 introduction videos from Crash Course Statistics, which I'll be using throughout the semester. It's a really excellent resource for kind of quick tidbits that really give a 1,000-foot view into some of the things that we'll be covering. But I think that their visualizations and animations are really nice and that they do a good job covering a lot of the key concepts. So these videos will mostly help when it comes to the midterm and final, when we have more conceptual questions for the written part of the exams. So anything covered in these videos, the concepts will be covered in class and in textbooks, but it could be helpful to have these videos as well. The assigned readings will be for chapter 1, section 1.1 to 1.3, and also this great paper called What is the Question, which kind of goes into scientific theory and a lot of these different concepts. And we will have a Python demo that goes along with the textbook that we will go through after the slides. And there will be homework and it's shared on the Blackboard website where it'll be different data wrangling practices and some exercises from the textbook. So as always, please feel free to reach out on Slack. I've been really enjoying seeing all the different correspondence with questions. If you ever need help with anything, please just put it on one of the public channels and I'll respond. But also if you see a fellow classmate ask a question, feel free to jump in with your own ideas for how you would address any questions. So with that, let's dive in and I will share my screen and we will go through the slides. Alrighty. So concepts of measurement. I will always try to add a little snappy subheader for what it is that this concept that we'll be talking about really is talking about, and really about data and data preparation and how this can be used to really create some type of scientific theory that you can go off of, whether this is in a business decision or any aspect of understanding how things work. So throughout any contemporary human activity, there is data being created. Anytime you send a text, open an email, buy new shampoo at the store, there's a data point that can represent this action. So when we use this data at scale, we can analyze patterns and trends and make predictions about relationships and future outcomes. So that's where statistics can come in to make information from data in order to make better decisions. Would be the goal. So in this chapter, we'll describe various types of data and measurement scales of variables that are used throughout statistical analysis. So it's important to note that after obtaining relevant data, a considerable amount of time is used to inspect and prepare the data for analysis, sometimes known as data munging or data wrangling. From a survey in 2020, we see almost half or 45% of someone like a data scientist who works with data all the time, most of their time is spent on just data preparation tasks. Another component for data scientists involve exploratory data analysis, sometimes called EDA, where we cluster the data or find patterns useful to inform a decision. And we use statistics to create models of our data to validate a hypothesis or understand a problem better. And a large part of data science is interpreting our own analysis, such as articulating, why is this information useful? Why should anyone care about this? what insights can it provide? And so an important ingredient of a well-executed statistical analysis is to clearly communicate information into written and verbal language. Numerical results on their own, such as like a table or looking into the actual like data frame itself, are usually not necessarily useful until we accompany it with clearly stated actionable business insights. Before we get into the technical side of things, I want to start on the philosophical side, how we consider scientific theory, which really means how do we know anything about anything? What is known? How do we prove that something's been verified? We use logic and statements for a theory to become a fact. It must first be falsifiable. This means that it could be considered true or false, and that's where you create a different experiment to test this theory. So first, we derive statements to prove or disprove this theory. The falsification principle was proposed by scientific philosopher Karl Popper, and he proposed that for something to be scientific, it must be able to be proven false. If things are falsifiable, then they can be used in scientific studies and inquiry. So we use our observations to identify patterns that are then used to develop a hypothesis and inform your theory. And things can get more complicated though. Most scientific theories are actually based largely on probabilistic induction and modern inductive inference. And we'll get into probability and Bayesian methods as opposed to something that's frequentist, where it's like, let's see what this looks like. How often does this occur? And can we use this to then inform future patterns? But we'll get into a little bit of stuff later in the semester. But really, I just want to talk about what is a statistical model. And that is something that represents a particular phenomena in the world. We find that the world is best modeled by mathematical rules. Maybe not best, but it can be, which is kind of the interesting part of why any of this matters, is we can use these types of models to make sense of the world around us. So one book that I really love, and I would recommend it to anybody, is called Math Without Numbers. It's a great read and has many illustrations about how data and statistics can be used to inform the world around us. Here's just one screenshot from a page where it has a bunch of examples where different processes are visually described by a model, such as a simple harmonic motion describing vibration of a plucked string on an instrument. Can also be used to look at the length of a day. You have this kind of oscillation of a model of how these things work, or the average temperature over the course of a year. Thinking even like the height of a point on a rotating circle, levels of tides, and compression of a string. All these things can be modeled using statistics and math. But when we construct a model or theory, there's an infinite amount of information we can actually use to support or refute it. You can kind of come up with anything to say this is true and these are all the different concepts around it. But when we're practicing scientific theory, we should think about things as in parsimony, where like fewest number of parts needed to prove our theory. So William of Ockham, who was a logician and actually a friar, actually, I hope that's how you pronounce the word, but like a Franciscan friar in the year 1300, he defined this rule called Occam's razor, which states that complexity needs not to be postulated without a need for it. And pretty much that just boils down to, between two different theories, we should choose the simpler one. Fewest moving parts, that's really the key concept here. And this is something throughout the semester that we should keep in mind when we're developing some type of analysis, that the simpler solution is the one that is usually the one you should go with. So just because a model makes sense, it might not be the correct one. So here's an example. Also throughout this semester, I'll be perhaps referencing some code from Professor Bianco, who is a data-driven astrophysicist, professor, and also a professional boxer. Some of the content was inspired by her class, and I'll always give reference when it is derived from her content. I hope everyone can see this all right. Okay, just making sure that nothing gets cut off. Where were we? So when humans originally wanted to model the way the planets work. And this is from her slide, so I just wanted to share it with our class. So when humans originally wanted to model the way the planets work, all we had were observations. And as observations improve, the models must be able to continue to fit the data. So a new model that is much simpler may fit the data just as well as we started thinking about a geocentric and move towards a heliocentric model of our solar system. Geocentric models are natural, and from our perspective, we see the sun moving while we stay still. Bringing this back to Occam's razor, between two theories, we should choose the one with fewer parameters. And this is just one example of how thinking about the world around us, how many different ways we can think about it, we should go with the one that will stand the test of time and can continue to be proven true as we collect and observe more data. The data speaks if you know how to listen, is really what I'm trying to say here. But it's important to know what is the question. We can consider our statistics to be analysis as we move to summarize, interpret, quantify, and investigate the data. We can have several different types of questions that we want our data to answer. And that's why it's important to know the right question to ask. So some answers might be descriptive, some might be exploratory, inferential, predictive, causal, or mechanistic. Here's just a nice flow chart that visualizes how each layer of analysis can build upon itself to develop a model and test a theory. And throughout our class, you'll see the cadence. We start with kind of these understanding descriptive statistics. We'll get into exploratory, talk about inferential and predictive. All these things really build up on the foundation of the latter one. So one other note to emphasize is that research must be reproducible. This will be something that I talk about and probably mentioned in the last one when it comes to referencing someone else's code and being able to reproduce someone else's research. Just because you were able to find a model that fits your theory, if it can't be tested and validated by others, people are going to question the validity of your results. So this is actually just an interesting thing in research. There's a whole reproducible gap in a lot of research that's published. So being able to prove the same results when someone else runs the same analysis is a really key component to all of this. So throughout the semester, we'll ensure that our research is reproducible. And also making things open source. I'll be publishing all my code onto GitHub. So if someone finds a mistake that I made, having it be open sourced and open for critique is a way to progress and move knowledge forward. So we'll always be trying to, how can we validate the outcomes that we found? And so that was a lot of the philosophical side of like, why are we doing any of this? It's really to understand how the world works in a kind of grandiose type of level. But now for the practical side of things, we'll go through some of the fundamentals of statistics. So we generally divide the study of statistics in two main branches. You have descriptive and inferential. Descriptive refers to the summarization of important aspects of data, such as collection, organizing, and presenting charts and tables. Elements of summary statistics are provided, such as the mean and standard deviation. And we see an abundance of this type of information that is collected and published in our society every day. And things such as, what's the unemployment rate? How is the Dow Jones doing compared to the S&P? What are the birth rates? All, so on and so on. However, this represents only a minor portion of the body of statistical applications. In my opinion, the more interesting side of things is in the inferential side, and this refers to drawing conclusions about a large set of data. We take a population and analyze a small subset called a sample, and in order to draw inferences about the larger scope of the population. And we'll definitely get more into the details of this, but for now, this is all going to be more of an introduction to what we'll get into in a deeper granularity later in the semester. But here's what a relationship might look like between a population, which is defined as all members of a specified group, and a sample. And let's say for a survey about seniors' expectations about the future stability of Social Security, just as one example, we're trying to understand how do How does this specific demographic, what do they think is going to be the future stability of their potential support for their livelihood? So if you were a researcher and you wanted to know what are their expectations, you would take a sample of a population of this demographic. So you would define it, perhaps age 65 and up, and create some type of sample statistic from that, rather than calling every single person in this demographic, let's say just within the United States. That would be very costly, and you can actually take a smaller subset as a sample of this entire demographic, which would serve as an estimate of the population parameter, which is the percentage of all seniors who believe that Social Security is stable. And the reason we need to ask a sample, again, it wouldn't necessarily be feasible to call up all 83.9 million people in the United States that are over the age of 62 and ask them their thoughts. Even if we had a smaller population for a different experiment, there are limitations on the number of data points collected due to cost. So consider the use of other ways to collect data that maybe are more scalable, something like sensors to detect noise levels across a city. Even if we had a microphone collecting a noise data on every corner, it's not this continuous understanding of noise in every single nook and cranny. We're just taking a sample of what is the noise at this corner of the city compared to another one. And that would really still be considered a sample of the overall population of like, what's the noise in the city? So generally, sample data are collected in one of two ways, either taking a cross-sectional, which is a record of information taken at one point of time, and compare this with a longitudinal or a time series investigation, which would look at the same data point over a series of time intervals. So for example, a cross-sectional data point would be the average GPA of last year's students across the MBA program in the United States, compared to a time series or longitudinal, which would be the annual average of GPA students in the New Paltz MBA program. So we would try to compare this over time. As New Paltz MBA students continuing to improve over the years? Like, is it going up, or how is it changing? Like, how does this relate compared to the same necessarily like demographic of MBA students at New Paltz from the year prior? So one is really a snapshot, while the other will take one point and compare it to the future or to the past. And when you think of data, the first thing, oh, there we go, slide moved. The first thing that might come to mind is probably numbers. When you think of data, you might think numbers. But in reality, data comes from everywhere and can exist in multiple forms, such as network data, like you see in this image here, of like, how are all these different websites connected on the internet? That would be an example of network data. You can also think of text, where any type of language might be considered data, or photos using something like computer vision to create structured data from an image to classify, is this a hot dog or a dog, for example. So this would be considered as unstructured data. Any information that does not conform to a predefined row or column format is considered unstructured. So this would be like your images, your network data, or text. So compare this with structured data, which is much more straightforward in an explicitly direct usable format. That's your data tables, and that's really what we'll be working with in this class. When we work with data, we should think of our information in terms of variables. Any characteristic we are measuring is a variable. Marital status and income are examples of variables because both vary from data point to data point. We classify a variable as either categorical or numerical. Categorical is a type of qualitative data point that represents a category, such as color, gender, or a Likert scale. For data processing, we usually convert these categorical variables into numerical codes, which we'll discuss in later chapters. But really think about these as something that represents a category. If you're thinking about a survey, like when you usually give your, your gender, you choose between two categories. It's not a number like your age. So for Quantitative or numerical data, that would be more like your age, which is on a continuous spectrum where we use numbers to identify a distinguishing characteristic of each data point. And this could be discrete or continuous, where a discrete variable assumes a countable number of values, such as how many children are in the family or score of a game, something that's discrete, it's countable, you can use your fingers to count it. Whereas a continuous variable is uncountable because there are infinite values to count within the interval, such as the investment return or weight of a child. It's not necessarily countable because you have decimals that can go to an infinite degree of specificity, or thinking about like the digits of pi, where it can go on and on and on, but usually we round, you could say 3 would be countable, but the real value of pi is really not countable on your fingers. So we think about discrete and continuous. And in order to choose the appropriate technique for summarizing and analyzing variables, we must first distinguish between the different measurement scales. The 4 major measurement scales are nominal, ordinal, interval, and ratio. We start with nominal data, and this is any category that has no ordering or direction. All we can do is categorize or group them. The observations differ merely by name or label. An example would be the companies that comprise the Dow Jones Industrial Average, where this is company A, this is company B. Just thinking about how these differ, we're not comparing them in any meaningful way. Similar for gender, these are just categorical things. One does not have any type of interval scale compared to the other. Next, we move to the ordinal scale, which is a stronger level of measurement because we can rank them in addition to categorizing them. Although we're limited that the rank between observations might be arbitrarily represented by a number. So consider something like the Likert scale of, how clean was this bathroom? If you ever see those at the airport, it might scale from 1 to 5, where 1 represents bad, 5 represents good. But this gives us now more of a ranking where we can now create some type of inference that this bathroom's cleaner than this one. But it's kind of gets a little more fuzzy when you think, what's the difference between considered a 1 or a 2? Might be difficult to actually numerically represent or compare between these different bathrooms. So we're limited in being able to perform arithmetic operations such as addition or subtraction. And that brings us to the next level, where we can find meaningful differences between data points when we reach interval data. For example, think about the Celsius scale for measuring temperature. We know that 30 degrees Celsius is higher than 10 degrees, and the interval is meaningful and uniform across measurements. There are still some drawbacks to interval data, such as some arbitrary decisions are added, such as how does 0 represent a value? The 0 point of an interval scaled variable doesn't necessarily reflect a complete absence of what is being measured. Therefore, we cannot make meaningful ratios between the different data points, such as 80 degrees being twice as hot as 40 degrees. The ratio 80 to 40 doesn't necessarily have much meaning. Where when we get to ratio scale, that's where we get to one of the strongest ways to measure, because it doesn't conform to a standard scale and it can be compared between measurements. So 0 point is meaningful because it is now described as a ratio, and it's kind of scale independent. When we talk about those measurements on a thermometer, 80 being twice as hot as 40 degrees doesn't necessarily have the same meaning as having this type of ratio when we get to ratio scale of data. So when we have a ratio scale, all the characteristics of the other measurements can be compared in the same way. When we take an observation, there might not be an exact measurement available. We do this often without really considering about how it is a proxy or measurement. Consider when a police officer is questioning if a driver is under the influence of alcohol. While they can't directly measure your blood alcohol content to determine if a subject is legally drunk or not, the officer might use observations instead, such as signs that would correlate with intoxication. They might not have the whole scientific kit to test your blood level at that point. So they might ask you to do a field test, such as seeing if your speech is slurred or if they smell alcohol on your breath. These could all be kind of considered like proxy data points to relate to direct measure of inebriation, for example. So we can consider these as variables that would predict the likelihood of a subject being legally drunk. And this is a proxy measurement. That proxy measurements are most useful if, in addition to being relatively easy to obtain, such as asking you or just smelling your breath is a lot easier than necessarily taking your blood. This is easier to do, but it's important that they're actually a good indicator of the true focus of interest. So we can consider the rings on a tree, to be a proxy for age. Historical documents are a proxy about our past, or using coral's structure to construct the temperature of the water when the coral grew. Like, these are all different ways we can better ascertain the true observation that we're looking for that might not be directly calculatable by just having something that is directly provided for you. We can safely assume that no measurement is completely accurate. There's a lot of uncertainty, and that's really important to think about whenever you draw conclusions from anything. There's different aspects we need to consider, because the process of taking measurements involves assigning discrete numbers to a continuous world. Again, thinking back to that example of if we're trying to measure the noise levels throughout the city, we're taking these discrete points to measure this continuous field of noise. When we conceptualize and quantify data, we must consider the degree of error that's present in a particular set of measurements. So classical measurement theory conceives of any measurement or score consisting of two parts. One is the true score, and the other is the error. We never know the precise value of the true score. We're using estimation. We use estimation for both quantities and try our best to maximize the number of true components while minimizing the error. And we can visualize how much uncertainty or error that might exist by using something like error bars in our analysis. And because we live in the real world rather than a Platonic universe that is strictly mathematical, we assume that all measurements really do contain some error, but not all error is created equal. There is random error, which is usually what we're okay with having. And there is other types of error where random error is due to chance, really. So just to give that definition, it takes no particular pattern, and why it's okay sometimes is because it's assumed that it'll cancel itself out over repeated measurements. For example, we want to take the true weight of an elephant, let's say. We would put that elephant on a scale, let's say 10 times, and the weight might differ slightly between measurements just due to inconsistencies in the calibration of our scale, perhaps. But however, the average observed weight should be constant. In order to be truly random error, it must be unrelated to the true score, and there must be no correlation between these errors. But in contrast, having something like systematic errors have an observable pattern and are not due to chance. For example, the scale might be incorrectly calibrated and all measurements are 5 pounds overweight. So we'd start to see this skew in our data that isn't representative of just kind of like random chance of things not necessarily being exactly to the point decimal the same every single time we put this elephant on a scale. And this relates more to measurement bias. Bias can enter a study in two primary ways, during either the selection of data or in the way the information is collected. So thinking about the scale having a 5 pound bias, that would be on the way the information is collected. But thinking about bias when you're taking a survey, if you're trying to ask all the seniors, how do they feel about Social Security in the future, and you only call from this one town, you're going to have probably a likely bias compared to if you're really trying to sample for all of the United States. We need to make sure that you have a distribution of the population that is represented in your sample. And This gets into a lot of other aspects of just, I use these targets to show the difference between having bias and precision in your different measurements. And likely there's always some type of bias, either like how you're analyzing things, how the data was collected, and what insights do you draw from it. So it's really important just to define what are the assumptions I'm taking, what are my own bias that I'm inflicting on my analysis. One example I just wanted to bring about, which is interesting, called survival bias. This is a well-known bias where you actually only look at the data points that remain over time. And a popular example of this is when the United States Army in World War II wanted to know how to protect their planes. They wanted to know where are the planes most vulnerable to gunshots so that they can better, defend these vulnerable parts of the plane body. But they only looked at the planes that returned and that were, had the bullet holes that they can analyze. When they plotted out where the damages were occurring, it was concentrated around the tail, body, and wings. But what could go wrong if they put all their efforts in protecting just these areas? Well, as I just mentioned, they're only studying the planes that returned in one piece. Had they measured the planes that didn't return, they would have been able to see the engine is the most vulnerable part of the aircraft. And once hit there, planes went down and they weren't able to have the plane return back home to have the damage charted out. So this would be an example of how the data was collected on this very biased data set. So it's good to consider any bias and the level of precision in your measurements underlying your data analysis. And we can consider the difference between precision and bias using this target representation on the right. The measurements might be precise as they continue to have an accurate measurement. Similar with the elephant's weight, over time will get more precise as we continue to sample. But all the values, if we had the imprecise measurement, we can think of that 5-pound difference will continue to be there. And that would be a biased example. So we can also have unbiased and imprecise measurements that might be considered random error, and biased and imprecise measurements would be an example of our survivorship bias. As noted earlier, we spend a large amount of time just inspecting and preparing the data for analysis, and most data in the real world is messy. It's not always straightforward, cleanly provided in an Excel data file. So throughout our work in the textbook, most files will be tame, and that'll just help us, understand these concepts. But in the real world, things are a lot more fuzzy, and it will still be a challenge to work with the data that we are going to have in our class, and how to best inspect and wrangle and explore the data. And we will now go through our first Python demo to show how some of these techniques will show how to import, how to count and sort the data, in addition to a few different ways we can handle missing data, which, thinking about how nothing's really perfect, we have to think about when there's missing data, what do we do with it? And thinking about with our measurement scales of maybe like a sensor data, maybe a sensor was broken, but we still want to understand like what is the overall area of noise in this area, but you're missing a sample data point. So how do we fill in missing data? Again, most data will be incomplete in the real world with missing values and also erroneous data points. And a handy way to think about missing values, or we call it like null or not a number, is to think about toilet paper rolls. So if there is paper on the roll, that represents that a data point was there. This is different than if all the toilet paper is used. That could be meaningful to say there's no toilet paper left, or 0. Compared to this, when there's no toilet paper roll at all, this would be a missing value called nan or null. Again, nan is not a number. And this stands for when it's not really 0 because it's just not anything being there in the first place. It would be imprecise to say this is 0 or there's no toilet paper left. There's really just nothing there. And compare this lastly to an undefined value, which isn't really going to be a concern for us because it gets kind of more into like infinite things and doing more arithmetic that created an undefined value. But we can think of this as just not any toilet paper existing. Like there's nothing there. All right, so with that, we will get into our demo. And I'm going to stop this recording just in case folks want to go back just to the Python part. It could be a little bit easier to manage. So let me go to our video.